So now I want to evaluate another improper integral. This one's the integral from negative infinity to 2 of 1 over 4 plus x squared dx. So the first thing to do with these improper integrals, and we know, by the way, we know it's improper because of this infinite limit of integration. So if one of your limits of integration is infinity or negative infinity, that's considered one type of improper integral. And I'm going to talk about another type in a later video. But here's this first type that we're looking at. And when we evaluate this limit, we need to start by replacing that infinite limit of integration with some, we call it a dummy variable, something like that. Seems kind of mean, but I'll use t this time. So the limit as t approaches negative infinity of the integral from t to 2. And again, and I'm not going to work on graphing this actual function. It's a little more complicated. But just thinking about your x-axis, well, here's the y-axis. But we're trying to integrate this thing from negative infinity to 2. So the curve here, if you graph it in using Desmos or something, let's see, if x is 0, it's 1/4. And that's the minimum value of this denominator. Well, anyway, the graph looks something like this. You can just take my word for it. And so if we're trying to integrate this thing from negative infinity to 2, well, that's an unbounded region. The integral would represent the area of that region. So instead, we say, okay, well, that's an unbounded region. I can't look at that area, but if I set up, let's say we set up a boundary here and call it t, and then allow t to approach negative infinity, then we're dealing with finite area. And so then we can determine whether the integral converges or diverges. So we integrate from t to 2. When we put limits of integration here, we always want lowest to highest in terms of area anyway. So from t to 2 as t approaches negative infinity, as this boundary here slides out towards negative infinity. Okay, so once you get it set up as a limit, then you need to find the antiderivative. Maybe this integral rings a bell. That's the hope. In the past, we used an integration formula for integrals like this. If you recognize an integral of the form 1 over a squared plus u squared du, then the antiderivative is 1 over a arctangent or inverse tangent of u over a plus c. So in this case, u is just equal to x, so du is just dx. A is equal to 2. And we can apply this integration formula to write the antiderivative. So this is the limit as t approaches negative infinity of the antiderivative is 1 over a, which in this case is 2. This is 2 squared, so a is 2. And u is equal to x. So 1 over 2 arctangent, or to save space, I'm going to write it as inverse tangent of u over a. And this is evaluated from t to 2. So this is equal to, let's see, the limit as t approaches negative infinity of 1/2 inverse tangent of 2 over 2. I guess I'll write it out. Minus 1/2 inverse tangent of t over 2. Okay, but so this right here is inverse tangent of 1. And to evaluate these inverse trig functions, you have to think, you're kind of working your way backwards. If you recall, the restricted range for inverse tangent is negative pi over 2 to pi over 2. In terms of the unit circle, it looks like this. And so we're looking for when in that interval is the output of the tangent function 1. And that's true at pi over 4 radians. Tangent of pi over 4 is equal to 1. So this is equal to pi over 4. Okay, so I've got limit as t approaches negative infinity of 1/2 times pi over 4 minus 1/2. Okay, I could have made this happen a little faster, but oh well. Inverse tangent of t over 2. So this now is just a constant, pi over 8. So let me just put that in front here. Minus, and now I take the limit, I only have to take the limit of the part that involves t here. Limit of a constant is just that constant. So this is just pi over 8. The 1/2 then is going to be just a constant coefficient. And now all I need to consider is the limit as t approaches negative infinity of inverse tangent of t over 2. Okay, but that's something I do want to talk a little bit about. I'm looking for my eraser. Here it is. So we need to evaluate this limit right here. I'm going to use this space, I suppose. Okay, so we've gotten this far. Actually, let me write down what we have at this point. So we know now this is equal to pi over 8 minus 1/2 limit as t approaches negative infinity of inverse tangent of t over 2. Okay, this is where we stand. Helps to recall the graph of inverse tangent of x, which looks like a sideways tangent graph. Keep in mind, so with inverse functions, we reverse the roles of x and y. Y equals tangent of x has vertical asymptotes at x equals pi over 2 and x equals negative pi over 2. So notice how I said x equals pi over 2. So with inverse tangent, it becomes a horizontal asymptote at y equals pi over 2. So the graph of y equals inverse tangent of x has a horizontal asymptote at pi over 2 and another one at negative pi over 2. And again, I mean, it looks like a tangent graph knocked on its side. So as x approaches negative infinity, because look at this, go back to where we are with the limit here. The limit as t approaches negative infinity, the negative infinity divided by 2, this is just approaching negative infinity. It's decreasing without bound. And so what we need to think about is inverse tangent of negative infinity. So as the argument approaches negative infinity, the value of inverse tangent approaches this asymptote at negative pi over 2. So this right here approaches negative pi over 2. So we're going to get a finite number out of this. This integral does converge. Pi over 8 minus 1/2 times this limit, which it turns out is equal to negative pi over 2 because of that horizontal asymptote. So this is pi over 8 plus pi over 4. If we get a common denominator, so multiply by 2 in the numerator and denominator there, I have pi over 8 plus 2 pi over 8 gives me 3 pi over 8. So the integral in this example, I mean, it's fine if you just box 3 pi over 8 for your final answer. But so the overall outcome here is that this integral converges to 3 pi over 8.